great to see everybody here after 2 years of lockdown and COVID. And it's nice to be able to get to see old friends and colleagues again.
Doesn't it?
If we all jump to the lifeboats, it's okay.
So, firstly,
We are working our way.
That's another sort of energy sustainable technology that sort of is great but works against us. It also burns the grass in my yard.
Thank you. Good to see you today. Yeah. When Russ asked us to stand up, if we were not from the UK, I stand up. You can see that from the accent. But I can be considered Londoner for the short and long term, and my family are Londoners. So I am an academic just around the 3 bends from the river in South Kent at Imperial College. I dedicated my career to study fires, all types of fires. And today I'm going to be telling you something that we have learned from study facade fires. 3 things that I hope you take with you today is I try to prove to you that facade fires are a blind spot caused by innovation. I'll tell you later on why. I would tell you how important it is, the cavity in understanding facade fires. And then I will just tell you some of the work that we haven't finished, so I cannot show you the conclusions, but I can tell you already what we are doing, and then you can ask me in a few months about the conclusions. First is I'm a scientist and I am an engineer. I'm both of them. But today I'm speaking to you as a scientist. This is important because scientists create knowledge and engineers use that knowledge to help society. Although those of you who are engineers or are in the fire safety world, I 100% support your task. But today I'm speaking as someone that tries to find knowledge. And then I just don't keep it for myself. That's not very useful. I actually broadcast it to whoever wants to listen and learn, and then hopefully this knowledge will be combined with previous knowledge, and we will help have a safer world. So I will start today. I don't know if when Russ asked me to speak, I don't know how many of you were thinking that today I was going to tell you the ultimate theory about facade fires, and I was going to just tell you all the little formulas that you can use. I start from the beginning. We don't know. I don't know. And I am convinced no one knows. It's one of these really complex problems that we are facing in London, but in the rest of the world. And when you call scientists, they call us and say, hey, scientists, tell me. And the answer was like, fascinating problem, let me look at it. It will take me about 10 years to give you something that you can use. In the meantime, I am sorry. And this is not just me, this is about 1,000 of my colleagues all around the world trying to look into this. It takes time to solve complex problems, you know this. And scientists, we are particularly slow. Not because we are slow people, it's because the process is slow. But I will tell you what we know, at least particularly from our point of view. Some context. This is, unfortunately, life in this planet is finite. We are all going to die. In the year 2011, The Guardian published this spider web, which are the causes of death in the UK. The most dramatic ones are the ones that are way too early, or the accidental ones. If you try, you're not going to be able to read it. I did it on purpose, okay? But you see the black arrow over there? Okay, that little dot on the red spider, that's the red is accidental fire deaths. They're not meant to happen. They're happening too early, and that dot is fire. It is about 2.1% of the fire death in the UK, of the whole country. We are slightly more than drowning, and slightly less than food ingestion. And for example, when you look into cause of death because of falls, falling in the stairs, falling in the street, falling in your house, fire is 16 times smaller. This is the context. Now, we're all here for fire safety, right? So now, if we look back in time, the best database that exists when you want to look back in time, by far, is the American databases, then followed by the British ones. But the Americans go much farther. It's almost 100 years of database. And every single year is of decent quality. Obviously, some years are better quality than others. You can imagine that in the 1880s, the process of collecting data was not as good as it is now. But everything together, this is as best as it gets in this planet. We will have to go to a different planet to get something better than this. So look back in time, okay? how bad it used to be. And the UK is no different, and any European country is no different than this. So we've gone a long way, and it was a lot of hard work, okay, for many people in this room and the previous and testers, into getting it at the point where we are in the UK, which is 2.1% of fire deaths. Now, I have a contradiction for you. At least it's a contradiction to me, okay, as a person that studies fires, right? So we humans, mostly because of engineers, but we humans are addicted to plastic. You know, plastic doesn't have a good press in the last decade, right? I'm a mechanical engineer. We do consider plastic, we call them polymers, a wonder material. But in this decade, it's not going too well, okay? It's related to oil, not good, and it's related to waste, and not good. There is another issue that most people don't talk about, I do talk about, is that every single polymer known to man, to humans, is flammable. Some of them are extremely flammable, and they are actually not legally allowed to be next to people. You only can put in a satellite and launch it into orbit, or you can actually, or some of them are very little flammable, but it's still some level of flammability. And we have this exponential addiction to polymers, plastics. Look around you, we are completely surrounded by them. And all of them are flammable. Now, don't worry, you know we are safe, okay? Now, the question is, we have a lot of polymers and a lot of flammability in our environment. When we look into our homes, our offices, and our factories, the level of flammability that we have inside, the amount of fuel that we have inside compared to what we had 20 years ago, 40 years ago, 100 years ago, is no comparison. It's now much higher. Yet, I looked into this recently, we did this, we haven't published yet. This is an analysis of the fire death, of the number of fires in London. This is specifically to this city, the city of London. The London Fire Brigade gave us access to the database. This is the number of fires, and it's straight down, literally. It is very little actually noise. It is just going down. Well done, London, okay, everybody involved. Well done, London, because this is really going in the right direction. Impressive. Now, I don't understand this. We have always more fuels and not stopping, and we have, at least in London, less fires. So this plot, the plot to the left, to the right, is used to people to scare us and to call us into action, to do more about fire safety, because our homes are extremely flammable. The other plot is used by other people, maybe governments, to say, don't worry, everything is fine. Right? And I find myself in the middle, thinking, I don't know, today I'm going to wake up and look into the left. Well, no, today I feel bad, I'm going to look into the right. And the reality is there is no contradiction. There are three things that we are seeing here. One is, I'm going to tell you each of them, and it's related to facades. One is the layers of fire protection. The other one is fire inequalities, and the third one is blind spots. Layers of fire protection, we are all in this room involved in at least one, probably several, if not all of them, layers of protection that we call upon as fire professionals to bring safety into our buildings, our homes, and our factories. We all have our preferred layer of protection. We always have one that we have spent more time, it's our business, it's our dear one. But the key is that all these layers are important, or these layers are considered at least when a building, a home, or a factory are being installed, right? And these layers are obviously prevention, not to have a fire to begin with, which means you can have flammable materials. That's okay, it's legal to have flammable materials, just don't put them next to the ignition source. Or don't put a material that is very flammable in excess next to an ignition source that is very powerful, because then the combination of the two of them will lead to a fire. So we have prevention. If we have failing prevention, we have detection. We have to detect it as soon as possible so we can do something about it. Then we have evacuation and compartmentation, and then we have, at the end, structural resistance. Okay? And all this is very important. None of these layers is perfect. Some of them have more holes than others in different countries, and the number of holes in the layers are different. The combination of all the layers is what brings safety. They call it safety in depth. It's an old, the Swiss cheese approach. It has many different points of view. So this is part of the success. This is actually probably the key to the success of a 2.1% fire death in the UK, and this massive drop in number of fires, and this massive drop in number of fatalities. There is another reason why there was this contradiction between the plots. One is that I am talking today right now about the UK or with data from London. This is not what happens in the rest of the world, and Ryan Mitchell, Dr. Mitchell has already alluded to this. There are many, many places, actually most places in the planet Earth, where they are not as lucky as we are. They don't have layers of protection. Their layers of protection have way more holes than us, or they actually don't even have the concept of safety because they are so worried about something else that they cannot worry about safety. For example, when we look into the statistics, fire causes 5% of the accidental death of injury-related death around the world. Compare that 2% that is produced by war. So actually fire is actually worse than war in bringing tragedy to humanity. The other reason is blind spots. And I'm going to make the case that Facade is a blind spot for us. It's an innovation blind spot. It's a blind spot because I'm going to be using the collective we, in the planet, we humans in the planet, we didn't see this coming. Now, in the particular case of the UK, which is not unique to the world, is we have a cladding crisis, which means that now we realize now that we've been making buildings that were excessively flammable. Excessive about, we can discuss it, regulations, measurements. We now believe it is too flammable. It has to be reclad, okay? How do we get into this? Are we the only ones in the world? No, we are not the only ones in the world, but we're the first ones in this country that actually are making things about it to solve it. That's the crisis only happens when you realize about it. So it is a blind spot because this is the city of London. Again, the last few years, at the bottom you have fatalities. This is the spot where there is no fatalities that year in the city of London, and this is the injuries. And you have the bottom here will be no injuries. And you can see that connecting them in chronological order, the city of London, it is going in the right direction. Incredibly, the slope of that curve is not going to get there, but it's going towards 0 fatalities and very low number of injuries. Most years, right? What happened in 2017? We have Grenfell. Why is it that we didn't see Grenfell happening, we as a collective set of people in the planet Earth? Is because it is a high-risk scenario with low probability. It is not going to happen often. Okay? When you look into the database, I'm going to show it to you now. These are rare events. Probability is low. The consequences are immense because they are tall buildings and people are actually sleeping in them. So you have low probability and low probability and high consequences. They still give you a sizable risk. In particular, this is actually high risk. But we can't learn from them because they don't happen often. This is what becomes a blind spot. So people who use these databases like I do to rate, to drive safety, we say, oh, we're doing so well in London. We just, I don't know, keep doing what we're doing because we're doing great. That is driven by high-frequency fires. That is not an approach that is valid for low-frequency, high-consequences fires. Why do we have this blind spot? Because of innovation. The fact that our buildings are better, maybe not that the last decade, that's up to debate, but on the planet we evolve and our buildings are getting better. They're getting more comfortable, they're getting more affordable, they're more reliable, they are better buildings. That is because there is innovation, fast or slow. In the construction industry, innovation doesn't come too fast, okay? But the innovation is coming. New materials, new designs, new way of thinking, new spaces. The dreams of the architect are the nightmares of the fire engineer. And the lag that appears between the innovation arriving, oh wow, new material, I love it, I love how it looks, and the fire safety community being able to understand what is the fire hazard and the fire consequences of that innovation. The lag starts to increase. And we decrease the lag when we see a lot of those fires, okay? But if this fire is not happening often, as it happened with facades, then the lag becomes to be large. And what we know now, and I can tell you this because I am one of the members in the fire safety research knowledge, there is a massive gap. I mean, we really don't understand facade fires, and these buildings are all around the planet. So hopefully I've convinced you that we have an innovation blind spot for many things. Lithium-ion batteries, one over here, that's another one. It's an innovation blind spot because these fires happen rarely. When something happens rarely, then that's what happens. Timber, green roofs, you say it, okay? I'm not saying that they aren't safe. What I'm saying is that they have a tendency to become blind spots because we call upon understanding when rarely they happen. So, facades. It is not new, right? Many of you are probably aware of many fires that happen with some years. Francis just showed us some of the fires, but there is one that happened in 1975. This was before I was born, so I consider it to be ancient from my point of view. Okay, this is an ancient fire that happened very close to the UK. Okay, it was Isle of Man. It's culturally and regulation and political a twin, a little brother of the UK. And this was a very dramatic, catastrophic fire. 50 people died, families on holidays, and it was a facade fire. These were innovative facades that allow this leisure center to replicate the Mediterranean summer in the British Sea. And it was far spread, and we could not understand it, to the point that we don't understand it now. And actually, people even forgot that this was a facade fire. It was revisited after actually what happened with Grenfell. Summerland is not the first. With our students at Imperial College, we spend an incredible amount of time looking into media and newspapers and obviously Google, and mostly within the English language search, and we start to look into buildings and evidence of facade fires, where the actual facade itself was involved in the fire. And what we see is a trend like this. Obviously, some years are more or less, but we see is clearly going up. It's obviously going up because there is more buildings, because the construction industry loves facades of this type. I'm going to show you now why. The facade, I don't know this. As an engineer, I definitely don't do facades. So facade engineers tell me is one of the most complex, or probably actually the single most complex part of a building. It has to do absolutely everything that people care about. First one is how the building looks. So the architect is going to ask you about it. It is going to control moist. In the UK, it's quite important, right? The moist, because it's in excess or because there is not enough when you are in a hot place. So you have to control the arrival of moisture. And obviously comfort for thermal insulation because it's cold or because it's hot. And the wind is going to be there, especially if it's tall. And you're going to have a weight because the facade itself we don't want it to be too heavy. And obviously it has to have fixtures internally, and it controls the light, and it has to protect us from the sound outside. And also, it has to be safe. So what has happened, it has become this blind spot because people were worried about all these things that really drive the construction world and fire safety. We thought we had it covered, but actually what we discovered too late that we were not. There are many types of facades. There are hundreds. It took us an incredible amount of time to actually understand even the nomenclature of a facade wall. But I think I can tell you that our focus will go on these three. Probably actually even two of these, of all the facades that are. These are facades that can have combustible materials. They don't have to, but they could happen. Okay? The one at the top here next to me is the Ethics facade. It has a substrate, typically made of brick or concrete, and then there is insulation. The insulation has to be there, otherwise you are exposed too much to the elements. And then the insulation itself is not very pretty, so you cover it with something, with plaster, with concrete, with something. And the fact that there is an insulation means that combustible materials can be present. There is no cavity. Then you have the sandwich panel, which is like the Ethics, but it doesn't have the substrate, it doesn't have the brick or the concrete. And then you also have, and you can actually have, an outside that could be metallic or clad. And then you have the REIN screen, the one that has become particularly worrisome, which is an innovation because it has a cavity. And the cavity revolutionizes many of the objectives that I told you before. It actually does the moisture in particular completely different, and actually adds this clad, which is a completely independent aesthetic element. It's not aesthetic itself, but it can be act as aesthetic. And that means that you can change the texture, the color, the feeling, the shape. You can do fancy things with the building. So these are the main types. And we want to understand the flammability of them. It is now obvious, I think, to everybody, it was not to me a few years ago, that they behave completely different, the two of them. If you put the same materials in each of them, but one has cavity and the other one has not, their behavior is different. So as a fire scientist, at the most fundamental, what I want is what everybody in science has been doing for a very long time, is that we go into the lab. Our labs are very small, okay? Ours is in South Kensington. If we could sell it, we would buy a castle in Scotland, but that's not going to happen. So we go into our smallest labs, and we do burn a lot of things, and we have hundreds of things, but they're very small, right? And then we have a visit from the fire brigade, and the fire brigade thinks this is cute, no? Because you are burning little things. They are putting their lives at risk with big fires, right? That actually were saving people and property. So when a scientist is also an engineer like us, we do our tiny little cute experiments, but we actually want to apply that knowledge into the real world, right? If we are not engineers, we just stay in our little cute experiments. But in my group, we are engineers, so we actually really want to go into the real realm. So we want to do what is called bottom-up. So we do a lot of experiments, we learn a lot, and then we say, well, how will these materials combine themselves into a facade, right? And then we try, maybe we do a few experiments, maybe we do a computer model, maybe we do observations like Mary Frances has done, maybe we ask people. There are many ways that we can do this bottom-up approach. Bottom-up approach is extremely slow, extremely slow. And it is happening as we speak. Many research labs around the world are doing the bottom-up approach. It would take about 5 years. There are some results coming, but it will take more years.
Tall Building Fire Safety Network delivers high-quality safety management training for anyone involved in the fire risk management of high-rise or tall buildings. Recognised by the Institution of Fire Engineers, we've been delivering fire safety training since 2011, and many organisations rely on our training for gaining competence in this field. Sign up for our training courses and conferences in 2023.
There is another approach, which is the top-bottom. Now, the top-bottom is controversial because, for example, trying to learn from specific fires cannot be generalized, or at least requires a high level of evidence that it can be generalized. So what we think is like, who is looking into the flammability of facades? Not like a piece of foam and a piece of ACM, no, like facade systems. Who puts them together and burns them? It's like testing houses around the world. We have some of them here in the room today. So we went to them, every single one of them, in different languages, and we said, you've been in the business for a long time. You have to have an amazing database of facade fires, of all types of facades and all types of behaviors. And they all say, yes, that's why we're calling them. Can I have access to it? And they say, no. Okay. And it's fine. We never took it personally, because we knew that they say no because it was written in their contracts that this data belongs to the people who is paying for this. And the people who were paying for this was always people with a conflict of interest or with a business reason. So they could not give it to us, and it was a pity, and we felt sad about this because we thought there are millions, literally, of fire tests in the planet stored in different places. Okay? If we put them all together, knowledge emerges. There is actually artificial intelligence, statistics is meant to, you take a lot of different things and then you interrogate it in a way and knowledge emerges. It's like, it would be amazing to have it. No, we're not going to have it. So then at some point, we met ITB in Poland. I consider them to be our heroes. They are absolutely heroes in fire science. They are a testing house, partially belong to the Polish government, partially private. And they are scientists, which is crazy. They hired not just engineers, but they actually hire scientists. All of them have PhDs, and they actually do commercial work, but they also do science. And they said, we have a little footnote in our contract, tiny little footnote that no one has realized about, that allows us to give you access to our database, as long as you don't say, Guillermo, whose product is burning. I said, fine, I have no interest whatsoever to say whose product is burning. I just want all of it all together. They say, okay, well, they opened the gates, and they said, we have 300 tests for you. Incredible. The only thing is, at that time I was a little bit concerned, is the Polish standard. I said, oh, is it related to the ISO? No. Oh, is it related to the British? No. The NFPA? No. DIN? No. Japanese? No. It's the Polish standard. It's what Poland has come out with, and it works really well for them. And at the beginning, I was very concerned. This is the Polish standard. It's about 3 meters tall, 2.8. It's an actual facade that you built in, about 2 meters wide, and it has a fan, and actually you have to pass it 3 times. At the beginning, I thought, this is weird. Fan, it's not too big, it's not too small, you have to pass it 3 times. Wonderful, absolutely wonderful. You should go and take a look at what they're doing in Poland. So because they give us access to 300 tests that were actually what the industry of Poland in the last 10 years, I think it is, was interested in knowing. It was some of them learning, some of them exploring, some of them actually getting a certificate to build. We started to see trends. We saw knowledge coming out. For example, this is the percentage of the facade. How many of all the ethics ones, all of them are green. That means all of them pass the Polish standard. The sandwich panels, all of them 100% were green. All of them passed the Polish standard. And then the only failures that we started to see were actually when we look into the REIN screen. Green means all the criteria of propagation of a fire, flame height, debris falling, cavity being formed, all of them were actually not present. So this was a safe facade. If it's orange, if it's yellow, it is at least the facade was started to spread the fire itself. If it's orange, it was actually quite a big flame, and if it's red, pretty much everything happened. So the fire spread, the flame was large, and actually even pieces of debris started to fall. And you can see that we only saw failures in the REIN screen. We did not see failures in the sandwich panels, and we didn't see failures in the ethics. Obviously, this doesn't mean, that ethics, all of them, no matter what you do to them, they are safe. That doesn't mean. What it means is that there is something going on in the REIN screen that doesn't happen in the other ones. So I'm not saying that sandwich panels ethics are safe. I'm saying they are safer than the REIN screen. There is something about the cavity. The cavity, what is the combustibility of the cavity? The cavity doesn't have combustibility, it's air. It's just one of the components of the fat triangle. But what's in the cavity? Actually, there is nothing in the cavity. It is actually air. The presence of the cavity augments tremendously the flammability of the facade. We remove the cavity, the facade might still be flammable or combustible elements, but the flammability, the hazard that it produces, tremendously drops down to the floor. Now, it doesn't mean that if you don't have a cavity, you're safe, okay? But it means that if you have a cavity, the level of worrisome should be multiplied by 100. So this is a blind spot. I didn't know. I actually had to go on the long route of research to learn this. If someone had told me it is about the cavity, I would have paid more attention to the cavity. This can also be seen is you look into now, we go to the REIN screens, the ones that have a cavity. These are only REIN screens, okay? And then we look into, of all the facades that we had, the number of facades that we had in the database, what are the types? So you can see, for example, that all terracotta did fine. There were not that many. There were only like 2 of them. All the compressed basalt did fine. All the wood polymer composites did, which is flammable, did fine. All the ACP, or ACN called in the UK, the aluminum composite materials, A2 did fine. The cement board, all of them did fine, except one. And that one, if you look into it, it had precisely a phenolic foam. It was not a mineral wool. You start to look into the ACP FR, which is a different level of fire safety, and then you can start to see the colors appearing. Very few are green, and when you look into HPL, high pressure laminate, you can see the colors start to rise up. So I'm not saying that every single terracotta facade is safe, as opposed to every single HPL facade, but there is something about the HPL that is actually not present when you look into the cladding of the terracotta. And also, it also is very interesting something here is that these were tests asked by the industry in Poland. Poland is a very good representative of the construction industry in Central Europe. They were asking for a lot of tests here, where the colors are. They were asking less for the experiments where the colors are green. So they themselves, the industry, was trying to learn, trying to push the limits more into the realm that we know had more of a flammability. And that's up to the little bit that we have learned that I wanted to share with you. Now we're doing something else, and I would like to tell you something about it. It's not finished, so there are no conclusions. Inspired by Professor Howard Emmons. This is one of the founding parents of fire science. He was in the US. He passed away in 1981. He was a professor of mechanical engineering in Harvard. They knew how to hire in Harvard. So he did many things in his career, but one of the things he did is he was very unhappy about the standards of flammability around the world. So what he did is he bought a very large set of material panels, and then he set them around the world. I think more like 15 countries. Send it to Germany, send it to Spain, send it to Italy, send it to the UK, send it to India, and he said and pay each of the companies and says, test the flammability of these panels, okay, and rank them from very flammable to very little flammable, and send me the results. You don't want an ISO certificate. No, just literally, just rank them. Obviously, some of them are very flammable, some of them are not. Oh, this is really easy. So he put everything together. Obviously, he was talking to the Spanish engineers, and they were like, our standard is superior. And the Germans were saying, what are you talking? Our standard is superior. And then every single one around the world were thinking their standard is superior, and every single one of them was different. When he put them all together, he proved scientifically that the result was equivalent to throwing a dice. Literally random, okay? So we humans, maybe the Germans are amazing, maybe not, but we humans as a whole, in 1886, we didn't know how to measure flammability. People said, that's not very flammable. And the other one was coming and was like, what are you talking about? That is extremely flammable, okay? So his study, he just published the study and showed it to the world, led to a wave of rationalization of standards. And what we have today, we like it or not, it used to be worse before Professor Emmons did this. So we thought, we love Emmons. We want to do like him. So what we did is, we're doing this as we speak. We chose 5 standards around the world there are wonderful standards around the world for measuring flammability of facades. We just have to choose 5. We didn't have money for more. So we choose 5. We choose, obviously, the policy standard because we think that ITV are our heroes. And the ISO because it's international. When a country doesn't have one, they go for the ISO. NFPA, America is a big country with influence in many countries around the world. The DIN because the Germans. And obviously, we are in the UK, we did the British. When you put them in order, they go from tiny and cute, but they're actually taller than me, to absolute monster. Okay? So you ask each of the members of the regulation committees that came with this, and they tell you, this is superior. What are you talking about? This is superior. What are you talking about? This is superior. What are you talking about? This is superior. And we could have months of conversations of the little details of what makes it superior. No, it's the wood. No, it's not the wood. It's the thermocouple. No, it's the height. No, it's the L. Good. So what we did is we chose these 5 standards. We managed to find a lab around the world that with our tiny little budget was able to do the 5 standards, not just 1 or 2 or no, the 5 of them. And then we choose 5 facades. We wanted to do 25, but we only have money to do 5. And we are testing each of these 5 facades on each of the 5 standards, and we're putting everything together. And maybe it will be an Emmons moment when the result is equivalent to throw the dice. Most people think that that's not the case. Or maybe knowledge will start to emerge. It will be obvious that everybody knows which one. Maybe you can actually do it now, right? This is an ethics with a render and mineral wool. You think this is the most flammable facade, or you think it's the least flammable facade? This one is ethics with render and EPS. This one is this 3 are REIN screen with HPL. This one has mineral wool and phenolic or mineral wool. You all have opinions. Some of you because you are in the business. Some of you because you have seen these facades actually burning. But how many have seen these 5 facades and 5 standards? I think no one. And if someone is one of the speakers that comes later on. So we put everything together. The results are very interesting. I cannot show you the conclusions. It will lead to specific stories being cast in stone. What we can tell you is that it's not obvious. Some trends start to emerge. Obviously, if as an ethics with a render and mineral wool where the flammability is tiny, minuscule, we are seeing that actually everybody agrees that it's not flammable. But when you start to increase the combustibility of the material, there is a significant divergence in what each standard is saying. Yeah, I'm finishing. And this is what we are most proud. It was very difficult to get the NFPA rig and the BS rig inside a lab. We couldn't, so we actually built them outside the lab in Poland with our heroes. And as we speak, literally as we speak today, they are running them in Poland little by little, consuming our budget for the sake of science. So, conclusions, I'm finishing. The first one is that we do have to catch up with innovation. For our scientists, people like me, we are very slow. I'm sorry for that, but we need to catch up with innovation because otherwise there will be a gap between safety and what actually is being built. That unfortunately, maybe you are unhappy about this outcome. There is no theory. There is no computer model. There is no experimental series that will allow us to understand the flammability of a facade from first principles. Other things exist, but not the panacea of solutions. The knowledge is tremendously fragmented across different countries and different institutions, and there are massive gaps in this understanding of facades fires. That facades are systems, not materials. So our tiny little experiments in the lab, which I love, are not going to help us because it's not about the materials, although it is a part of the materials. It is going towards the system, the real engineering system. That there is this massive role of the cavity that most people didn't know about. So the cavity, a material that doesn't have combustibility, the presence tremendously increases the flammability of the facade, and that more research is coming. So I just finished to say thank you to some of our researchers that were more involved in this, and obviously our sponsors. I'm very thankful. Unfortunately, we don't have time for questions, but you can ask me at any time. Thank you very much.